Okay, let's continue. Um, uh, in close complement, when we do the addition of binary value, let's take an example here. Is a few examples, three examples here. In fact, uh, in decimal system, we have 3 plus 2. We know the answer is 5. But in the tooth complement notation for 3 is 0011. Tooth complement for 2 is 0010. In decimal system, you can easily do the math, which give you the answer of 5. But in binary system, we can do the same. We do the binary addition on the right hand side here. So 1 plus 0, 1. 1 plus 1 is 1, 0. So 0. And we carry 1 to the previous, to the left binary. So 1 plus 0 is 1. And 0 plus 0 is 0. Okay? Now, 0, 1, 0, 1. This is post complement notation. And what kind of value is represented by 0101? Is decimal value of 5. So this 5 and this 5 is consistent. Okay? So in post complement notation, we can do correct decimal computation in this example. In fact, not only this example, all the example, all the, I should not say all, because we will see pretty terrible problem later. Okay, now let's keep on this second example. Minus 3 post complement notation is 1101. Minus 2 post complement notation is 1110. Okay, now in decimal system, everybody can do that. We get minus 5 as our answer. Now in post complement notation, we just do the binary addition. 1 plus 0 is 1. 0 plus 1 is 1. 1 plus 1 is 1, 0. We got 0 here. But we carry 1 to the previous binary. Now, 1 plus 1 plus 1. In English, or in decimal system, we call it 3. But in binary system, we don't have 3. All we have is what? Is 1, 1. So we have a 1, 1 here. But as we just mentioned, since we are doing in 4-digit binary system, if we got an extra 1, we just truncate. We just take it off. Okay? Now, 1011 represent what? Represent minus 5. So minus 5 and this minus 5 is consistent. Now, we have a positive value plus positive value. We have negative value plus negative value. Plus plus, we got plus. Minus minus, we got minus. Now, if we have a positive value plus a negative value, which is also easy, everybody knows the answer, is 2. Now, in post complement notation, 7 is represented by this. Minus 5 is represented by this. And we do binary addition. 1, 1 become 1, 0. So we carry 1 here. 1, 1, 1 we call 3, but we cannot represent 3 in binary system. So in binary system, we represent as what? 1, 1. So this is the one on the right. The one on the left, we carry over to previous one. So 1, 1 is 1, 0. So we have 0 here. And we carry a 1 to the previous location, previous digit. And 1, 0, 1 is 1, 0. So we got 1, 0 here. Again, 4 digit. We got 5 digit. The extra digit is truncate, is delete. Now we get the binary of 0, 0, 1, 0. What is 0, 0, 1, 0? Is 2. So this 2 and this 2 is consistent. Now, we are going to talk about the problem with 2's complement notation addition. Okay? The problem with addition of 2's complement notation. Okay? Okay, before that, this line on the PowerPoint say the advantage of 2's complement notation is the addition of any combination of size number can be accomplished using the same process, which is good. Internal logic design, internal IC design, okay? Internal design a circuit to do addition and subtraction. You can use the same circuit. A minus B, you can do a circuit of A plus negative B. Okay? So you convert B into minus B and using the addition circuit design. And you can accomplish subtraction. Now, so 2's complement notation, this is one of its advantage. So here is a subtraction problem of 7 minus 5 is the same as what? As addition problem of 7 plus minus 4. Okay? So the same circuit or the same algorithm or the same IC design can do both addition and subtraction. Now, so if we can build a circuit that can negate a value, what's negate mean? Negate means change the sign. We have positive 5, we change it into negative 5. We have a negative 6, we change it into positive 6. Okay? This is called negate. Okay, change signs. And a circuit that add 2 value can do both addition and subtraction. In addition, multiplication is just repeating the addition. 5 times 4 is equal to what? 5 plus 5 plus 5 plus 5. Totally 4 times. Okay? So just one circuit can do multiplication also. And also you can do division. Okay? This 6 over 2. Okay? You can just 6 minus 2 minus 2 minus 2 to count how many times your remainder remain positive. Okay? So this just one circuit can do addition, subtraction, multiplication, and division. Okay? From these 2 circuits. Okay? For 2 circuits. The addition of 2's complement notation and the negation and the negation. Okay? And the negate circuit. Okay, now As I mentioned previously, tooth complement notation has a flaw, has a problem. But in fact, it's not tooth complement notation's problem. Okay, it's the limitation of computer memory. Because it's finite, because it is finite, it is inevitable. Okay, we come into so-called overflow problem. You can always find a number bigger than a given number. Okay, I say it again. You can always find another number which is bigger than a given number. Okay? Computer memory is limited. Say, for example, we use 1 byte. How many values we can represent? 1 byte is 8 bit. How many values can be represented by 1 byte? It's 2 to the power of 8. Is how many? It's 256. Right? Because 2 to the power of 10 is 1020, 10 and 24, 1024. And 2 to the power of 8 is divided by 4. So we got 256. Now, you only have 1 byte. You're going to using 1 byte to represent value, represent number, or represent integer. How many integer you can represent? 256. Okay? So, in fact, in tooth complement notation, you are using 8-bit. To implement tooth complement notation, the value you can represent is 127 plus 127 0 negative 128. The total number is 256. What is overflow problem? Is that please tell me whether or not you can say positive 128 into this 1 byte tooth complement notation. The answer is no. The answer is no, because 1 byte tooth complement notation, the largest number can be represented is plus 127. 128 is bigger than, is larger than 127. Therefore, 128 cannot say in this 1 byte limit location. In this tooth complement notation, the value can be accurate, safe, or accurately manipulate. Is between plus 127 and minus 128. Positive 128 cannot be fit into this system. Negative 129, no. Negative 139, 130, no. And so on, and so forth. Positive 129, no. Positive 200, no. All this number were causing this 1 byte tooth complement notation system a problem, and this problem is called overflow problem. You have bucket which can hold 10 liters of water. You put in 11 liters of water, 1 liter of water will be flow out of the bucket. And this is similar to this case. You put in a number which are too big or too small for the numbering system to accurately save. This is overflow problem. And one good thing about tools complement notation is easier to identify overflow problem has occurred. Okay? How you detect such problem occurred? As we mentioned, tools complement notation can do addition, subtraction, and multiplication, okay, and so on. But one problem we will encounter most likely is the addition. When suppose we are still using 4-bit to represent the tools complement notation. Okay, 4-bit tools complement notation. The largest one, the biggest one is 7. The smallest one is -8. So anything behind this range, 7 and -8, is so-called overflow. Now, suppose you are doing a mass of what? Addition of Jesus. Let's see if we have, okay. I remember do a setup of oh, so-called pound resistor. Here I have a pen. It's supposed to respond to pen only. When the tablet detect the pen is near the surface of the panel, I should ignore the touch of my finger. But it seems to not work properly. I remember I do I don't know. It's kind of annoying. Okay? Now, let's come back. Where do we go? Okay? Here. Now, let's do a little math. You know, in 4-bit system, when we 4 plus 5, we should get 9. But you do a math of tools complement notation. The result show you -7, which is a totally wrong answer. because if you add two numbers, both of them are positive numbers, you should get a positive value. But in here, you get a negative value. In two's complement notation, when you do the mathematical addition of two positive numbers, and the answer you get is negative, which will indicate you got an overflow error. As I say, the overflow error is not anybody's fault. It's the limitation of the memory space you are using. Of course, we are only using 4 bits. You can increase the number of bits to implement two's complement notation, to widen the range. Currently, 4 bits only, the range is from +7 to -8. If you have 5 bits, the range will get bigger. If you have 6 bits, even bigger. Okay? If you have 32 bits, the range is even much bigger. And the bigger of the range, the less chance you will encounter this overflow error. But however, it cannot be totally eliminate the problem of overflow error, because no matter how big of the memory space you are using, you still will have a limited range. Okay, the range of the value is limited. Let's go back here. 4 plus 5. Why we get 7? Let's go back to the table. 4 plus 5. Okay, 4 is here. 5 is here. Now, the bit pattern of two's complement notation for 5 is 0, 1, 0, 1. The bit pattern for two's complement notation of the two's complement notation for 4 is 0, 1, 0, 0, 0, 1, 0, 0. Now we say we can do binary addition of two's complement notation. So these two complement notation, one is for 5, one is for 4. Now we add them together in order to get the addition of 5 and 4. Okay, now we add 1, 0, 1, 0, 0, 0, 1, 1, 0, and then we get 1 here. 1, 1 is 1, 0. Okay, now 1, 0. This is a value of what? 1, 0, 0, 1. 1, 0, 0, 1 is this here. It represents -7. So, in two's complement notation, 5 plus 4 become -7, which is ridiculous. Okay? Ridiculously long. It's a long answer. Why is long answer? Because we have an overflow problem. How we know it's overflow problem? Because we have a positive value plus a positive value, and we get a negative value, which is obviously mistake here. Okay? So when you have two numbers which have the same sign, and after multiplication you got a different signs. When you a positive value plus a positive value, and you get a negative, overflow error, you can be easily detect. When you have negative value and a negative value and you add them together, you get a positive value, which is impossible, which indicate an overflow error. Okay? So, in order to detect an overflow error, it's easy. Okay? There are two kind of situation. Okay? Two positive number get a negative value. Two negative value get a positive value. It tell you an overflow error has occurred. So when you run into a program that show you overflow error, then you know what's an overflow. Then you know something about memory size, something about the mathematics, the computation in your program is doing number, doing value too big, okay, or too small, okay. So this is the advantage of two's complement notation, which can easily detect so-called overflow error, and which is very important. When I was a freshman in this department, and I took Introduction to Computer Science and we write program, and the computer reports tell me overflow error. We have completely no clue what happened. We don't know what's overflow error. At that time, we don't have Google, okay? We don't have the internet. We don't have anything to find out, to check. What does it mean by overflow, okay? But today you have all kind of resources to help you to learn almost everything, okay, from the internet. Okay, so you guys should do a better job than my generation because you have much more resource than my generation. Okay? So don't let me down, okay? So this might occur when adding two positive numbers or adding two negative values might occur so-called overflow error. How to detect, which is easy, by checking the size bit. Okay? If you have a 2-0 size bit and you got a one size bit, which is overflow error. You have two size bit is 1 and you got size bit 0, and this is error. This is error. Okay, so we must aware the danger involved here. Okay, the danger involved here. So in fact, in C we have a different variable type to handle integer. The difference is the size of the variable, okay? And we will talk about that later. Hopefully not too late, because we are late, because we are using English, okay? So in actual implementation, how many bits we are implement two's complement notation? Normally, also in Visual Studio, C++, or Visual Studio C, it uses 32-bit, so it's quite large. So two's complement notation, the biggest number can be accurately represent is this guy. I don't want to read this number out because it's 2 billion something. 2 billion, okay? Two billion is what in Chinese is 20 亿, okay? Is 20 亿. So it's quite big, okay? 32 bit. But for normal usage, such a big number, 2 billion, should be sufficient. But there's no guarantee. This number will always sufficient for your application, especially for science project. Now, let's get on, okay? The next topic we are going to talk about is Stirling fraction. What's fraction? In Chinese, we call 小数 or 分数, okay? Now, for example, this is 1,500. We can use so-called scientific notation because it's too troublesome to write so many zeros. Okay, 1,500 is easy because it's kind of easy because you only need to put a 20 here. But if the number is so big, okay, it's bigger than the space I can write on this PowerPoint space. What I'm going to do is using so-called scientific notation. So in scientific notation, we just kind of, it does not allow me to erase because I write too many zeros outside the space. Okay. So 1,200 in scientific notation, we can write 1.5 times 10 to the power of 3. So I guess everybody know how it works, okay? So it does not require me to explain too much about this. And 0.015 is 1.5 times 1 times 10 power to the negative 2, okay? So this is scientific notation for this guy. This is scientific notation for this guy. And the good thing about the scientific notation is it is the exponential part. Okay, this is save you a lot of time of writing zero or counting zero. Okay, because this number exponent indicate the number of zero. Okay, indicate the number of the actual value, the relative position of this decimal point. Okay, specify the decimal point related to the actual value. Okay, so this is scientific notation. Now, in computer, how to say a number with fraction, with a 小数点 or 分数. Okay? Now, what we can do is using a very scale example to illustrate how computer to implement this fraction. We call it floating point notation. And the simple example here, we're using only 1 byte of storage to do the demonstration, okay, to do the illustration. Now, we divide this 1 byte. We know 1 byte is equal to 8 bits. Okay, now this 8 bit, we further divide it into 3 parts. Okay, 3 parts. The first part is 1 bit, is here. We call it sign bit. Sign bit indicate whether the value is non-negative or negative. Okay? If the sign bit is 0, it means the value it represents is a non-negative value. Why call it non-negative? In fact, so-called non-negative means positive value or 0. Okay? So it can be greater than 0 or equal to 0. Okay? It can be either one of these cases. But if the sign bit is 1, it means this value is negative. Okay? Now, the remaining 7 bit is using for representing the negative of this value, the absolute value of the value you are going to represent in this 8 bit. Okay, so the first bit represents signs. Okay, 0, it means positive or 0. And if sign bit is 1, means this value is negative. Now, the second part of this 1 bit, is here, which contains 3 bits. And this 3 bit, we call it exponent field. Okay? It's similar to here. 10 to the power 3, 10 to the power negative 2. Okay, it's similar to here. The difference is this exponent is not based on 10, it's based on 2. Okay, it's based on 2. That's wrong. You guys will understand what I meant. Okay, now. The last 4 bit, we call it Mantissa field. Mantissa field is similar to the 1.5 here. It's similar to 1.5 here. Okay. Repeat this again. The first bit is sign bit. The following 3 bit is exponent. The last 4 bit is Mantissa. Okay? Remember, okay? Now, let's use an example to understand what's going on here. Is suppose we have this 8 bit, and what kind of value this 8 bit represent? If we're using the floating point notation. Now, this guy, you check the ASCII code, it will give you a symbol. Okay? The same bit pattern, if you interpret as a SS notation, it will give you an integer value. This pattern, you interpret as a 2's complement notation. It also gives you an integer value. But here, the same pattern, 0, 1, 1, blah, blah, blah. We are going to interpret as a floating point notation, which of course is just 1 bit, 1 byte, 8 bit. Now, using this kind of convention, okay? First one is sign bit. The sign bit is 0, so sign bit is 0. Okay, means this value is either positive or 0. And in fact, it is not possible to be 0 because in the following bit, no one is 0. Okay, the Mantissa part is not 0. Okay, so it's impossible to be 0. It is a positive number. Now, exponent contain the following 3 bits. Now, the exponent here is what? Is 110. So exponent is 110. Now, Mantissa is the last 4 bit 1011 1011. Okay? Now, what we do is just separate this bit pattern into 3 parts. First part, sign bit. Second part, exponent. Third part, Mantissa. Okay? Now, first part, second part, third part. Now, we extract the Mantissa part and place a radical point. Again, you guys remember what is radical point? In decimal system, we have a decimal point. In binary system, we have a radical point. Okay? They are similar, but they are in different kind of numbering system. The radical point is for binary system. Okay? It separates the binary value into a whole value part and a fraction part. Okay? It's a radical point. So this radical point, by convention, okay, by the rule set by some kind of standard of computer science, we put the radix point on the left of the Mantissa part. Mantissa part is 1011, so the value is 0.1011. This, let me erase it. So you can see this 0 here. And the radix point here is put on the Mantissa part. The leftmost binary value here, 1011, 1011. We put a radical point on the left of this 4 bit. Now, the next step, exponent part, is 110. Now, 110 we are going to use in SS notation of integer. And the SS notation with 3 bit is SS what? SS4 notation. Okay? Because we know 3 bit 2 to the power of 3 is 8. And we divide by 2 is 4. So I'm not going to repeat how to explain the SS notation. We spent enough time on explaining the SS notation last week. So 110 is using SS4 notation. Now, what's the binary value it represents? 116, 110 is 1 times 2 to the power 2, plus 1 times 2 to the power 1, plus 0 times 2 to the power 0. This is equal to what? 6. And we have an SS4 system with the SS notation, and the 3-bit is SS4. 3-bit is SS4. I'm not going to explain it again. Okay? Now, SS4, so 6 should minus 4 to get a value of 2. Now, 2 is exponent. It's similar to scientific notation of 10 power to x. So, dot 1011 times 2 to the power of 2. So it means we have to move this radical point to the right by 2. So by 1, we get 1.011. By 2, we get 10.11. Okay? This is, we move this dot to here. 1 position. And to here, we move 2 position. And since the exponent field give me a value of 2, we need to move 2 position. In fact, it's getting bigger, okay? 1011. So, what's the value represented by this 1 byte floating point is 10.11 based on 2. The base is 2. So how we interpret this guy in base 2 system is 1 times 2 plus 1, 2 to power 1, plus the 0 times 2, 0, plus 1 times 2 minus 1, plus 1 times 2 minus 2. And this is what? We know this is 2. We know this is 0. We know this is 1/2. We know this is a quarter, 1/4. So mathematically, this is represent 2 and 3/4, right? So 2 and 3/4. So this bit pattern interpreted as a floating value is in actual numbering system is 2 and 3/4. Okay? Now it seems we have to take a break. Let's take 10-minute break.